So we're starting distance time graphs. This goes right hand in hand with our motion that we've been doing, right? So now we're going to see what that looks like on a graph. So we're going to work through this presentation together. And then we're going to have some practice to do in the days to come. So our distance time graphs are going to be like what we did in math, plotting on a graph. Okay? But time is going to be across the bottom, and then distance is going to be up the side. And you'll see what I'm talking about as we get into it. Okay? Did I say time? Distance over time? Yeah. Time is across the bottom, distance up. So distance over time. You can remember it that way. If you call it a distance time graph, then it's distance over time. See that? It shows an object's motion. It shows how long it takes an object to travel a certain distance. And so the x-axis, everybody do your arms out. Remember, x is horizontal. That's going to be your time frame. Your y-axis, arms up to form a Y, like we're going to sing YMCA. Y-axis is your distance. So it's distance over time. Distance over time. And you can see that this line here that they've plotted, let me get my pointer going. It starts at 0, 0. The time starts at 0. And what are we measuring in? Hours. And what kind of distance are we measuring in? Kilometers. Okay. So it's 0 kilometers and 0 hours. And then we move up from there. Now remember, a steep hill means what? It's an increase, right? But is it slow or fast? That's pretty fast, right? The steeper the hill, the faster you're going. What about when it sits still like this? It's just staying still. It's not moving. So for this amount of time right here, it just sat still. Now, it is Halloween almost. And so I'm going to give you an analogy to think of. Have you ever seen on TV, doctor shows and stuff, where it shows somebody's heartbeat and it says beep, 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 and the line goes up and down, up and down, up and down. Well, then they die, and what happens? Beep. It's a flat line. So if you see a flat line, I want you to think nothing is happening. Okay? It is sitting still. And then you can see it started moving again right here. Okay, does everybody see that? Let's move on. Distance over time graphs. What can you calculate using a distance and time graph? You can calculate speed because the distance traveled divided by time is speed. This would be kilometers per hour. So we can measure it from here to here, or we can measure it from here to get the average distance over time. Right? So distance over time, or distance divided by time, equals speed. And we took notes on that. But it's kind of like, remember we said division as a fraction? Distance divided by time is a fraction, right? And then if you divide it out, you will get speed. Does everybody understand so far? Okay, moving right along. Here is a distance time graph, and you have medium, slower, and faster. If you have constant speed, what does that mean? If you have constant speed, what does that mean, Maddie?
The speed is like, it keeps going.
Okay, if I'm going 60 miles per hour and I have constant speed, it means that I stay going 60 miles per hour. Think about if you set the cruise control on your car. You know what cruise control is? It makes you go a constant speed. Constant means the same thing over and over, right? So if you see a straight line like this, it's a constant speed. Now, we mentioned this a little bit already, but the lower the increase, the slower it goes. So that's why this pink line is the slower one. The yellow one's the fastest one, and the blue one is the middle one. And think about if Mr. Best is going to sled down that hill, we want the fastest hill, so we want the tallest one. Now, that might not always be the case. They might say, which is the slowest speed? And you think, well, which hill is not going to be so much fun to go sledding down? You need to sit up and wake up. The best part of waking up is Folgers in your cup. A straight line shows an object moving at a constant speed. We said that. If it's straight, the speed stays the same. The steeper the line, the faster the object's moving. Okay, if you're at home, you can't see what I'm about to do with my arm, but everybody's going to make a fast distance over time graph. Make a fast graph. What we're doing is holding our arm up pretty steep. Let's make a slow graph. Let's make a no motion graph. For those of you at home, you would hold your arm flat to make a no motion graph. Slow, medium, fast. We're not going to go straight up, okay? Slow, fast, no motion. Okay, good. So the steeper the line, the faster it's moving. And if it's straight, then it's moving constant speed. Next slide. I don't think we moved. Which object is faster? That one, the red one, or the green one? Which one is faster, the red one or the green one, Thomas? The red one. Now the green one's longer, and it still went the same distance, but it took it a longer time to get there, didn't it? Here you went 10, 30, is that 30?
Yeah.
You went 30 meters. Miles is MI. M is meters. We went 30 meters in 5, is that an S?
Yeah.
Seconds. Here we went 30 meters, but it took us 15 seconds. This is faster. Okay? We'll look at it one more time. So you would say if they have 4 lines, A, B, C, D, right now A is the fastest and B is the slowest. Now we could work this out. What is 30 divided by 5?
6.
So this would be 6 meters per second. This would be 30 divided by 15. 2 meters per second. Why? Distance divided by time. Okay, let's look at our distant time graphs here. Constant speed. This is our same graph from earlier. Speed equals distance divided by time. I'm going to let everybody have a chance to get out a piece of paper. When we do this work for distance over time, and I'm showing the people at home here, when we do this work for distance over time, I want to actually write the distance, and I want to put the actual distance over the time and make it be a fraction. Okay? And that way, then we can work it out from there. So if we look at the first one, I'm going to make it big. I'm going to work it out back here on the board, and then I'll show my paper. But let's work them out together, shall we? So what is the first distance? How far did we travel? And remember, distance is up the side. The yellow one goes to 30. And it doesn't tell what the distance is, but let's do meters. So on the top of our fraction, we're going to put 30 meters for distance. On the bottom of our fraction, how long did it take? What's the time?
10 minutes.
10 seconds. 30 meters over 10 seconds. Write it down. So I wrote 30 meters, 30 m over 10 s. What is 30 divided by 10? 3 meters per second. That's how we're going to write our answer. I'm going to write it up here so when I show it, everybody at home can see it. 30 meters, 10 seconds equals 3 meters per second. Because 10, 20, 30, 3. What? Okay, that was yellow. That's the yellow line. Let's look at the blue line. Did the blue line travel 30 meters? No, how far did it travel? It traveled 20, so we're going to put 20 meters. And underneath that, how many seconds are we going to put? 10. It traveled the same amount of seconds. When I write seconds, I like to put SEC. SEC, seconds. So 20 meters divided by 10 seconds is how much? 2 meters per second. And last but not least is the pink line. How far did it travel? 10 meters in how many seconds? 10 seconds. 10 divided by 10 is 1 meter per second. Okay, so let me exit and I will show you. Yellow was 30 meters. Where'd my pointer go? Hey, Lordy, I've lost my pointer. There it is. Let me get the pointer on here. Ha ha. So look right here. 30 meters divided by 10 seconds is 3 meters per second. 20 meters divided by 10 seconds is 2 meters per second. And 10 meters divided by 10 seconds is 1 meter per second. You good? Does that make sense to everybody? Remember, distance is y and time is x, so distance over time. Now, let's view No, not rename. Let's view, present. And we can move along. Stationary objects. Now, we already know what a stationary object looks like. A stationary object has a flat horizontal line. If stationary, now if it's ERY, that means it's like cards and stuff that you can write on, like a stationary kit, like you're going to send somebody to get wheel card. But if it's ARY, it means not moving. Your desk should be stationary. What does that mean? It shouldn't move. A flat horizontal line shows a stationary object. This means the object is not moving. Time keeps moving, right? 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Now, if I was talking about this in nature, I may say, I let my dog outside and he sat down. He did not move for 8 seconds. Here's the graph for it. He's just sitting there. Let's all be stationary for 8 seconds. Ready? Don't move. It's statue. 1, 1,000. 2, 1,000. 3, 1,000. 4, 1,000. 5, 1,000. 6, 1,000. 7, 1,000. 8, 1,000. Okay, you can move. That, we just acted out this graph. Okay? Evan. What about if something is speeding up? If something is speeding up, then it shows a line like this. And the steeper it goes, the faster the object's going. So you see it's going pretty slow right here. And then it starts to speed up. Okay? Is everybody good with that? If it was slowing down, it would look like this. Watch.
At some point I did this.
Okay, let's look about changing direction. From A to B, we see that the object moved from 0 meters to 60 meters. It would be like if I got up and walked across the room to over there where Lydia was, and then from B to C, I just stayed there. I just stayed over at Lydia's desk. Well, then from C to D, what did I do? I came back to my desk. Foster, from C to D, I came back to my desk. This is upper class. I don't know who named this graph. Upper class jogger chases pesky rabbit. So you go outside and you see the rabbits in your cabbage. And here's where you chase it away. And then you stand there to make sure it's gone. And then you go back to the garden. I mean, that's what it is. When you see a line like this, it's heading back to the starting point. Okay? So this is constant speed in one direction. At rest, constant speed back to start. A jogging graph. It's the upper class jogger chases pesky rabbit. Describe the motion of the jogger in each section of the graph. We already did that. Let's say it again for good measure. Right here, the jogger goes from distance 0 to 60 in 20, is it seconds? Meters per second, right? So 60 divided by 20 is 3 meters per second. And then the jogger stays still. And then same thing, 10, 20. So it was the same measure. Meters per second. What?
It says that B is on 30.
Huh?
It says on B is on 30.
Oh, it is, ain't it?
Yeah.
I went down the wrong line. So 60 divided by 30 is 2 meters per second. And then this line is steeper. Is it?
Yeah.
6, 50, 60, 70. Yeah. So 60 divided by 10, 20. This one would be 3 meters per second. So the jogger jogged faster right here than the jogger jogged over here. From this angle, it's harder to see that, but thanks for pointing that out, Jaden.
I'm glad I made it.
Now, here's a man walking a cat. I don't walk no cat. I might walk my dog, but I don't walk no cat. 2, 3. Where is that?
That's
12 meters.
That's
Okay.
12 meters, but 3 seconds.
The first 3 seconds is 12 divided by 3 is 4 meters per second. What's the man doing between 3 and 5? Standing still. Maybe the cat had to pee-pee. I'm just going to stand still right here and let the cat do its business. Then calculate the speed of the man between 5 and 7 seconds. Well, that's only 2 seconds, isn't it? 5, 6, 7. That's only 2 seconds. And he went from 12 to 0. So what's 12 divided by 2? 6 meters per second. What is the total distance that he moved? Well, from here to here, he moved 12, and from here to here, he moved 12. So that's how many meters? 24 meters. Very good. Draw a distance time graph showing your journey to school. Try to include different gradients to show different speeds. Remember, steep slope is fast, gentle, slow. Gentle, slope, slow. Okay. We're going to pretend. We're not going to draw your actual trip to school, but we're going to pretend that Miss Cindy has picked you up on the bus. Okay? We're going to pretend down here we're going to do minutes. Okay? 0, 5, 10, 15, 20, 25, 30, 35, 40. Does it take anybody 40 minutes to get to school on the bus?
Yeah.
Mm-hmm.
Because last year we didn't get there till 8, and I got there at 7.
Distance is going to be up here. This is time down here. It's minutes. And up the side here is going to be distance. And how do we measure our distance in this country? Miles. Aiden, you're going to have to stand up if you can't stay awake, son. So let's do miles like this. 5, 10, 15, 20, 25, 30, 35, 40, 45. Right here's where Miss Cindy picked you up. At 0, 0. That's your house. And say after she picked you up, the bus sped up. Then she stopped to pick up another kid. Then she sped up. Stopped to pick up another kid. Sped up. Stop to pick up another kid. Sped up and then constant speed. And you got to school. So this would be speed up. This would be rest. This would be constant speed. Now, is that really what it looks like? No. Eli, you are not on task. You need to cover that nose and shut that computer. But this is a good example, like if I was going to draw a graph of maybe how the bus does. Okay? But this would be brake really fast. Really, it should be like speed up, slow down, speed up, slow down. Like it would be more of a wavy. But this is good enough for all intents and purposes.
Well, you don't have to be perfect.
Okay, so moving right along. Let's get this called back up. I don't think we have too much more, like one more slide maybe. Okay. This is going to be our review, and then we're going to take a note. A straight line is what? The steeper the line, the faster the motion. A flat line is stopped, no motion. Okay, what's a curved line going up? An acceleration. What if it's a curved line like deceleration? What if it's going back down? It's returning to start, right? This doesn't show going slower. This only shows getting faster. Okay? But now we're going to draw some in our journal, so get ready. Alert the media.